Hello everyone, welcome to MECH 3313 Thermo-Fluids Lab at UTEP. This is your instructor, Naushad Arslan Islam, and today we'll be going over our part 1 of the first lecture, the study of centrifugal pump. So in this lecture we're going to be covering a little bit of introduction of the pump and types of pump, and then we're going to be getting known to centrifugal pumps and a little bit of characteristics of the centrifugal pumps such as priming, cavitation, net positive suction head, and performances. Keep in mind that knowing this would help you going into your experiment, and it will also help you to understand some of the things that will be covered during the class lecture. Let's talk a little bit about the pump. What is a pump? A pump is basically a mechanical device that imports energy to fluid. Now keep in mind, pumps usually import energy to liquid fluids. In case of gaseous fluids, those are called compressors. Pumps usually don't handle gaseous fluids. And the most renowned case or most known case for pumps are that you import mechanical energy to hydraulic energy. That is basically taking water from a lower level to a higher level. The very first case of pump was back in 2000 BC, where the Egyptian shadoof was discovered. That is basically a counterweight was used on one end and a bucket was used on another end to actually lift water from a well to a higher level. Then the next case was around 200 BC, where the earlier reciprocating pumps designs were coming out, and the world-renowned Archimedes screw pump is established back in that time. And going into fast forward into the 2000th century, we have a lot of these pumps, and you can still see the screw pumps, there's piston pumps, there's different kind of aerodynamic pumps, but we'll get into it. Let's go into the next slide. On this slide, we're going to be talking about types of pumps. Pumps can generally be divided into two broad types, rotodynamic pumps and positive displacement pumps. Positive displacement pumps are those where you'd have a chamber where you can have the fluid sucked into, and then a moving object would thrust or displace the fluid out of the chamber through the discharge valve. Well, these positive displacement pumps can again subclassified into either reciprocating action or rotary action. Similar to, you could talk about reciprocating engines or rotary engines. Very similar. So reciprocating pumps, they can again be subdivided into piston pumps, plunger pumps, and diaphragm pumps. And you can say that all of these have reciprocating action. So these pumps generally do displacement using reciprocating movement. Where the rotary pumps, you would have a screw pump, gear pump, vane pump. You can actually see that these screws, gears, vanes all have rotary motions. So you're going to be displacing that fluid using some kind of rotary motion. Now, keep in mind that positive displacement pumps are very high head pumps. They can produce really high head. Now, rotodynamic pumps, they impart the energy to the fluid by rotation. So you'd have some kind of rotating member where the fluid will come in, and then that rotational energy will be imparted to the fluid. Now these rotodynamic pumps, they can be subdivided into either an axial pump or a centrifugal pump. Now, rotodynamic pumps, they produce a relatively lower head, but uh, but they produce a very high discharge rate. So positive displacement pumps are going to be very high head or a very high pressure pump, but they produce very low discharge rate. And the rotodynamic pumps are going to be producing very high discharge rate, but the head is going to be relatively lower compared to positive displacement pumps. Okay, let's talk about centrifugal pump. Well, it's a rotodynamic pump, as you already know, and this is generally the pump that you see day in, day out. If you have a pump in your house, that is most likely to be a centrifugal pump. These are the pumps that you see all the industries, in all the agricultural uses. Maybe if you're looking around the university, and maybe if you're doing research and if you need water for some purposes, and if you're using a pump, most likely that's the centrifugal pump. These pumps, they basically transfer the kinetic energy of the rotating impeller to the fluid and converts it into a hydrodynamic energy. The rotation is generally provided by an electrical motor, but it can be also provided by some other kind of prime movers, maybe engines. In agriculture, or we can see that if there's no electrical outlet, there's usage of engines to move these pumps. Now, you can see on the lower picture that there's a suction pipe where the water goes in, and you can see the rotation of the impeller is shown there, and the water rotates on that impeller, and the impeller displaces the water from the center of axis with a centrifugal motion towards outward of the impeller blade, and it hits the casing, and then it goes out the discharge path. So since centrifugal motion is parted to the fluid, that's why it's called a centrifugal pump. Now these pumps are generally used for incompressible fluids, basically liquid fluids, and we know that incompressible means constant density, and centrifugal pumps can handle high viscous fluids. That means water, oil, honey, even on case of cold slurries, and in cases of other mixtures, uh, maybe like in paper industry, the paper and water mixture, the raw paper. So those kind of mixtures and very high viscous fluids, centrifugal pump can actually handle those. However, in case of positive displacement pump, they cannot handle high viscous fluids. They can only handle low viscosity fluids. Now, there are four main components of a centrifugal pump: the impeller, the casing, the suction pipe, and the delivery pipe. Now, how the centrifugal pump operates is that the very first step you do is priming, that is basically filling the pump out with water or whatever fluid you are going to use in the pump. Then you turn the impeller on with the delivery valve closed, so there's no delivery. Now the rotating motion of the impeller would start imparting energy to the fluid, and it will start displacing the fluid towards the impeller end, and will pour centrifugal motion to it, and it'll start hitting it into the casing. Now at this moment, if you start opening the delivery valve, the velocity head imparted to the fluid would start changing into pressure head. Um, the casing of the impeller, casing of the pump is designed such a way that it starts from a it becomes from a converging section to a diverging section. So as you see, the velocity would decrease, but all that velocity would change into pressure, and you'd get pressure head out of your discharge path. Now, as the water starts moving out from the eye of the impeller, that's basically the center of the impeller, a suction air or a vacuum is created there. Now, that vacuum actually starts bringing on the water from the sump to the impeller again. So basically, a negative pressure is created, and the water is sucked from the sump impeller. And again, the water is imparted energy by rotational motion and centrifugal motion, and it goes out through resistors. And that's how a continuous water uh, imparting energy to water keeps on going throughout the process. Priming. I talked about priming a little bit on the previous slide. However, let's discuss a little bit more about priming on this slide. The very first step for operating a centrifugal pump is priming. That is basically filling out your whole pump chamber, your suction side and delivery side with the fluid that you're going to use. If you're going to use water, or if any other fluid, then that fluid. This is done because you do not want any air to be inside your centrifugal pump when you turn on the centrifugal pump. The reason because the centrifugal force that is imparted to the fluid or the centrifugal force that creates the pressure inside your pump is directly proportional to the density of the fluid. So if you have a low density fluid in there, the pressure that you're going to create is going to be very negligible. So your pump will not work. So if you want to actually produce high head and have higher efficiency with your pump, you need to do priming. It has been seen that even if there's a little bit of air in the pump, you basically won't get any head out of the pump. Any there won't be no pressure head out of the pump. Or even if you get some, it'll be very low. You're gonna be operating at a very low efficiency. So one of the main aspects of our centrifugal pump experiment is looking for cavitation. Now, what is cavitation? It's basically bubble formation at your suction side due to pressure drop in your fluid. When the pressure drops in your system below the vapor pressure of the fluid, you see bubble forming on the suction side, and this is called cavitation. Now, if you look to the graph on the right, you can see a pressure versus temperature curve showing different stages of a matter. So you can see when the pressure is high at uh, at low temperature or at high temperature, you're gonna be either solid or liquid. But as your pressure goes down, even at a lower temperature, it's easier to get into the gaseous phase and produce bubbles. So the vapor pressure is when your pressure drops so below that on your pump operating temperature, you start seeing bubble formation. You start seeing your fluid evaporate in the pipe. The There's some very adverse effects of a cavitation. So the impeller is rotating at a very high speed. So when those bubbles go into the impeller due to cavitation, these bubbles start hitting the impeller and it starts making a lot of noise and a lot of vibration is imparted to the impeller. And when these bubbles explode or implode, they create shock waves which damage the impeller and they start eroding the impeller. And it also takes a toll onto your efficiency. So you're damaging your impeller, you're damaging your sealants, you're performing with a lower efficiency, so cavitation is very bad for the pump. So these these are some pictures you can see the damages due to cavitation, and there's a curve where you can see that the suction head and the discharge rate, and as cavitation occurs, how cavitation occurs and how cavitation increases. We'll be talking more about this in the class, so I won't be talking about this curve over here, but we'll be taking a better look about it in the class. And you can see there's a GIF image where you can see how the pump is shaking due to cavitation. Now, how to prevent cavitation? Well, to prevent cavitation, you have to have a net positive suction head available that is greater than your minimum required net positive suction head plus marginal losses. So NPSHA, which is available net positive suction head, has to be greater than or equal to NPSHR, which is the minimum required net positive suction head, plus margin. Now you guys may be wondering what's the net positive suction head. Well, let's go into that one now. So net positive suction head is basically the difference between the pressure head available at your pump inlet and the difference of that and the vapor pressure of the liquid that you're using. So it's basically pump inlet pressure minus the vapor pressure of the fluid. Now keep in mind that the vapor pressure of the fluid differs from fluid to fluid. For water, vapor pressure is different. For oil or some other fluid, the vapor pressure is something else. Now, net positive suction head available in PSHA. So this is the actual pressure available at your pump inlet, taking into consideration of all the losses. Now, at the pump inlet of your pump, you'd have before that you'd have piping systems where there's going to be vents, where you'd have instruments, you'll have some sensors, some kind of valves, some kind of strainers. All those result into some kind of losses. So the fluid, after overcoming all those losses, if the pressure that you're going to get at the inlet of the pump after that will be called the net positive suction head available. So basically it's the pressure at the pump inlet minus the vapor pressure after you taking into consideration all losses. How can you get that? You can get that by using Bernoulli's equation or the energy equations. So this can be found out using fluid mechanics physics. Now, pressure drop at pump occurs from frictional losses from pipes, your bendings, valves, instruments, transitions, all those. So on net positive suction head, you have to take into account all of these before you before you install your pump. Now, net positive suction head required. This is the minimum suction pressure required at the pump inlet to overcome cavitation. Now, this is generally given by the manufacturer. So, how this is accurate is the pumps are tested until cavitation is seen, and the NPSHR, the net positive suction head required, is basically the number that's taken when the discharge rate falls by 3%. So even if you don't see a bubble, if you see the discharge rate falling by 3%, you assume there's cavitation. And this is given by the manufacturer. So when you're actually operating the pump, you have to make sure that you have at least net positive suction required plus a margin because of the 3% drop on the discharge rate. So plus a margin that has to be at least met by the net positive suction head available. Now on the right, you can see how we can actually calculate net positive suction head available. So if you have a fluid at point 1 that has that's with pressure 1, P1, and then you have the pump inlet at the point 2, it is with P2 where you have some velocity V2. Absolutely P1 at P1 there's no fluid velocity, so V1 is equal to 0, and if the height between the 2 points is Z1, and if you have all the losses in the pipes, that is like summation of losses, so the energy equation would give that the pressure head P1 over rho G minus the datum head Z1 is equal to P2 over rho G plus V squared by 2G, which is the velocity head, plus all the pipe losses. All so now if you rearrange it and get all the inlets, pump inlets at one side and keep um, the P1 and the Z1 and the losses on the other side, you can write down that P2 and V2, that's gonna be the total head on the pump inlet. That's gonna be your net positive suction head available. So, excuse me, so that will be equal to your P1 over rho G minus Z1 minus your losses. Now the losses can be written as HIN, which is the internal head losses, plus HFI, which is the frictional head losses. Now, then net positive suction head available would be equal to P1 over rho G minus Z1 minus your losses, minus would be your vapor pressure, would be the P vapor over rho G. So if you have questions out of this, we're going to be going over this on the class again. So, but try to understand this and do come up with questions if you have during the lecture time. Pump performance. So we're going to be doing a little bit about pump performance also in the experiment. Basically pump efficiency, that's what we're going to be looking into. For centrifugal pump, the overall efficiency or the pump efficiency is basically the ratio of the energy imparted to the fluid to the mechanical energy imparted to the pump by the prime mover. So you can see the equation over there that the efficiency of the pump is basically the water horsepower divided by the shaft power, which is basically the volumetric flow rate of the discharged water times the head of the pump, produced head of the pump, divided by the rotational speed times the torque of the shaft. You can see the performance curve of the pump on your right. If you look into that curve, you can see it's a head versus discharge rate curve. So you can see from the head curve that as the discharge rate increases, the head decreases. That is because if, as you start to discharge more and more water and you increase your discharge rate, the capacity of the pump to take that amount of water to a certain height start decreasing. So suppose at 3 GPM, if the pump could take it to 80 feet high, at 6 GPM it would be able to just take it to 70 feet high. So it starts decreasing. Now, if you look into the efficiency curve, you could see that the efficiency starts increasing with discharge rate. Well, that is because you'd have more water going out, so you're imparting more amount of your energy to the fluid. So there would be an optimum point where you'd have your um, maximum amount of energy imparted to the fluid for an optimum head. That is called the best efficiency point. Beyond this, you'd see you'd have more water, but you'd have less head, so you'd be imparting less energy to the fluid. Um, and you could see the horsepower also increases with the um, discharge rate because you need the pump to work more and more hard to um, get to a certain level of to get this fluid into a certain level. So it makes basically all sense that your efficiency will start going down with increased discharge rate following the best efficiency point. Now this would be the experimental apparatus we're going to be using. It's Turbine Technologies Pump Lab. We're going to be talking about this more into the class. So that'll be all from me for this part of the lecture. So I'll see you guys on the class. Thank you.